student coordinator of Atal FTP. So I hope all had a refreshing break and are excited to continue our learning journey together. So it's my pleasure to welcome you to day 4 of online 6-day Atal Faculty Development Program on Introduction to Generative AI, organized by SJCIT. We are thrilled to have you all with us as we explore new ideas, share knowledge, and dive deeper into fascinating topic. So let us make today another enriching and productive day. Most importantly, I would like to welcome our resource person, Dr. Manjunath Kumar BH, for day 4 Atal FTP. We welcome you, sir. Let us begin with the day 4, session 7 on Introduction to Generative AI by Dr. Manjunath Kumar. I request Ms. Shweta to introduce our resource person. Over to you, ma'am.
Jai Sri Gurudev. Good evening, one and all. It's my honor to introduce today's speaker, Dr. Manjunath Kumar BH. Sir holds PhD in Computer Science and Engineering from VTU and having 23 years of experience in teaching, research, and administration in the field of computer science and engineering. Sir is working as professor and head of the Department of CSE at SJCIT. In addition to this role, Sir serves as Dean Academics at SJCIT, where he plays a crucial part in shaping the academic policies and strategies of the Institute. Dedicated member of professional societies, Sir is affiliated with ISTE and IEEE. His expertise extends beyond teaching into accreditation process. Sir has been instrumental in coordinating the NBA and NAC accreditation process at the institution. Sir also contributes significantly to the academic governance of various institutions and is a member of LIC for VTU, Board of Examiner for CSE and ISE at VTU, and has been a part of BOS for CSE at SSIT. Furthermore, Sir is actively involved in reviewing and chairing international conference and journals, fostering academic excellence and knowledge dissemination. In this current leadership role, Sir is the president of Institution Innovation Council at SJCIT. Sir research interests lie in the field of artificial intelligence, machine learning, and NLP. He has contributed significantly to these areas through over 20 publication papers in index journals and conference proceedings. Sir continues to inspire and mentor students, researchers, and fellow academicians, leaving a lasting impact on the landscape of computer science and engineering education and research. Now, I request you to take over the session, sir.
Thank you, madam. Thank you. Jai
Thank you,
Shri
sir.
Gurudev. Submitting my pranams at the lotus feet of our Mahaswamiji. I, Dr. Manjunath Kumar BH, Professor and HOD Computer Science and Engineering. It's my privilege to give a talk on the topic Introduction to Generative AI on Atal FDP on AI and security, current trends and future research. First, before starting the talk, I would like to thank SJCIT management and the organizing committee of Atal FDP for providing me an opportunity to give a talk on the topic generative AI. So let us discuss for maybe 1.5 hours about the topic generative AI. So let me to start my session with a question. What is an example of a significant technological innovation from the last century? Like, for example, if you are thinking like something that didn't exist when your grandparents were your age and now you are using every day, what may be that technological innovation you can identify? Obviously, the answer is ChatGPT. Because the artificial intelligence has been introduced in the year 1956, and it is known to all of us. But nowadays, AI and especially generative AI becomes the hot topic for everyone. And currently, irrespective of your role, maybe you are a techie or a teacher or any professional, or maybe you are belongs to a medical field, whatever it may be the role. Learning basics of generative AI is definitely a smart move nowadays. If you observe the diagram what I have shown in my presentation, earlier if you want to retrieve any data about a particular, if you want to know anything about any information, obviously you are supposed to read so many books or so many. You have to contact so many resources to collect the right information about a particular requirement. So nowadays, within a fraction of seconds, it is possible to collect data or any details or any information just by giving a correct prompt at ChatGPT. So why I'm using the word ChatGPT? What is this generative AI? How generative AI connected with ChatGPT? And AI is also I'm using here. And is there any connection between this AI, generative AI, and ChatGPT? Yeah, definitely. And so in my in this session, I'm going to give the relation between all these terminologies and how they are connected also. Next, moving on to the next slide of my presentation, you can observe here what are the topics I am going to cover in my presentation. As I told you in the previous slide, everyone can learn generative AI. Even if you spend 15 minutes daily for 8 days, definitely you can learn all the basics related to generative AI. And this is the roadmap for that. Introduction to AI, introduction to machine learning, deep learning, introduction to generative AI, and introduction to large language model, prompt engineering, and what are the ethical considerations in AI, and what are the challenges or limitations and future trends about generative AI. These are all the topics I am going to cover in my presentation. So this covers the basics of generative AI. Now, there is a question. Is there any relation between, or is it required, or we need to learn AI, or we need to understand AI, machine learning, and deep learning to learn generative AI? Yes, of course, it is required. As it is shown in the diagram, artificial intelligence is a superset. Under that, we have a subset called machine learning, we have deep learning, and generative AI is a subset of deep learning. So in my next slides, I am going to explain you how all these technologies are related. First, let me to begin with the artificial intelligence. Yes, what is AI? What is artificial intelligence? Let me to give the brief idea about AI. It is a very old term now, AI. It is the definition and everything. It is known to everyone. But still, let me to start with the basics. Let me take one example now. Suppose you have missed your dog and you need to find the dog. And if you want to find the dog, definitely you should be able to identify your dog first. And you should be able to make a strategy to find your dog. And you should be able to act according to the situation. Or like your brain should know what to do next, like as per the situation, because we should know if the dog is not available in the play area, it may be in the garden, or maybe it went outside. If it is raining, definitely we know maybe the dog is in the any shade area. So that strategy we should frame first. Okay, by making this strategy, we can decide, or we can think, our brain can decide where will be the dog. And after seeing the dog, also we should be able to identify it's our dog. It is possible only because of because so many calculations or decisions happen in our brain. Okay, so then finally we can find the dog. Suppose, consider the same situation. I want to make my robot a mission. Robot is not basically a mission. I want my robot to identify the dog, identify my dog. Is it possible? Yes, it's possible. How? We have to train our robot like it should act like a human with the intelligence. Then only it is possible it can find the dog. To find our dog, definitely we need to enable the robot to think like you, think like us, and act like us. And for example, if we give all the information about my living room, then definitely robot will search the dog in the living room. Even if I make any changes in the living room also, it should identify first it is my real living room. Then it can identify the dog. If it is not there, it can go to the play area or as per the strategy what we had given for the robot for the training purpose. So based on the strategy, it can identify the dog. So here, it is possible robot can identify the dog only because if it's acting like a human with intelligence. So with this example, what I want to I want to derive from this example is we can give a definition for an AI like artificial intelligence is like a human-like intelligence created in a machine. Here I have taken robot or a computer by human. So AI enables the computers to understand, analyze the data, and make decisions also without constant human guidance. These intelligent missions use algorithms, which are step-by-step instructions to process the information and improve the performance over the time. So this is what the basics about the definition of AI. Okay, and where is the requirement? Okay, for the AI. Okay, and now we will move on to the next slide. So there I am going to, you can see what are the real world examples of AI applications. Just have taken in the previous one case study I have taken, but these are the real world examples of AI applications. Most of us, we already experienced with all these applications like Amazon online shopping recommendations, Siri or Alexa as a virtual assistants, any feed suggestions using AI like in Facebook or in LinkedIn, and even Netflix also we have personalized recommendations using AI, and language translation or predictive text and autocorrect or fraud detection in banking. So all these are the very good examples, real world examples of AI. Now, coming to the next slide. So what are the different types of artificial intelligence? So yeah, the artificial intelligence, we have three types actually. Stage 1 artificial intelligence, stage 2 and stage 3. This stage 1 is an artificial, it's called as an artificial narrow intelligence. Can be called as machine learning also. So here, this intelligence is specialized in one area to solve a specific problem. So there is a specific problem. It is a narrow intelligence. It will solve only that specific problem. For example, like Siri, Alexa, or Google Assistant as a virtual assistant, as we are voice assistants we are using here. And if you go on to the stage 2, there we have taken a generalized to solve the problems, generalized problems, like a human being. Okay, so this is called as artificial general intelligence. So it can be called as mission intelligence also. Now stage 3 is again solving problem only, where the mission acts much smarter than the human being. So the best humans in all fields, if you consider, okay, your mission will perform much smarter than them. So this is called as artificial super intelligence. So these are the three types of artificial intelligence we have. So right now we are in stage 1. Okay. So in stage 1 only we have so many applications. Definitely to reach stage 3, so much of work should happen. So that's why it is a very trending area. Always there is a scope for the research in this area. Now coming to the next slide, I'm going to talk about the machine learning. Okay, basics of machine learning. So you can observe this diagram. Let me to consider my previous example only, finding a dog. But now for my robot, I have given plenty images of plenty animals. Okay, different animals images I had given, like cat images, dog images, and bunny images I had given. Now I have labeled all these images also, like cat, dog, and bunny. Now I'm asking the machine to identify the dog. So definitely it can identify the dog only the machine has trained with the features of dog. It means that to the mission we should train what are the features of each and every animal. So then only it can identify the animals based on the features like size, color, body shape, and sound, etc. Once this training is completed, the robot or a machine definitely will be able to identify the animals based on what we have trained. So it means that we are helping the machine to learn by labeling each picture with the name of the animal. So with this, I am going to define machine learning. So this is about the training. And once the training is completed, if I want to test my machine, okay, if I give a new picture of a dog, so actually this new picture was not, I was not used while I am training. Okay, I have used the dog images, but the new picture was not used in the training purpose. Now, still my robot should identify this as a dog only. So if it is possible, then the mission will identify this as a dog. Then only I can say the mission has learned something. Okay. So now explicitly I have not programmed to identify this image as a dog, but I have trained the mission with the dog images. Now, even though this dog image was not there in the training set, it will identify based on the features, it will identify this as a dog. So what we can say machine learning is a subset of artificial intelligence again, which enables machine or a computer to learn from the data and make the decisions. Okay, it will make the decision. Okay. So this is about the definition of machine learning and how the connectivity between AI and ML. Now there are types of machine learning. So we'll discuss it in the next slide, the types of machine learning. Mainly we have three types of machine learning, like supervised machine learning, supervised learning, unsupervised learning, and reinforcement learning. Let me just spend few minutes on these types of learning. So like supervised learning is like a teacher, like teaching a machine or a computer with examples. Okay, we'll provide all the pairs of all the input pairs and output pairs are given, correct output pairs are given, pairs of input and correct output is given while training the system, and input data is labeled here. So during training, what will happen? The computer adjusts its internal parameters to minimize the differences between its predictions and the correct answers. And success of this supervised learning measured by how accurately the computer can predict the correct output on new data, new unseen data. So based on that, success of the supervised learning can be measured. And here, the main goal is to make the computer to predict correct output for a new unseen input. And we have different examples, like we have already used the applications like spam email detection, fraud detection, facial recognition, or medical diagnosis. So all these are the applications which are designed and using a supervised learning technique. So there are some common algorithms which are designed using supervised learning, like linear regression, support vector machines, decision trees, and neural networks. So these are the supervised machine learning algorithms. Now we'll move on to the next type of the machine learning, is unsupervised learning. Your input data is not labeled, okay, and the algorithm it has to learn without any explicit examples of input or output mapping. So it uncover the hidden insights or patterns that may not apparent by just looking at the raw data. Okay, it has to uncover the hidden insights, and it requires less human intervention also, because in terms of providing labeled examples, making it useful when labeled data is scarce or expensive to obtain, then we can go with the unsupervised learning. So human intervention will be very less here. So here, what is the main goal? So definitely discovering, we have to discover the patterns, and we have to cluster the similar data. And if any anomaly occurs also, we have to detect the anomaly detection should happen. And next, coming to what are the examples of the applications which are designed using unsupervised learning, like customer segmentation, anomaly detection in cybersecurity, recommendation systems, social network analysis. These are the examples of unsupervised learning. What are the common algorithms which are designed using unsupervised learning, like K-means clustering, hierarchical clustering, or principal component analysis? These are the unsupervised learning algorithms. Okay, so supervised, there is a labeled data, unsupervised, unlabeled data is the input. Now we move on to the third type of the learning. It is a reinforcement learning. Here is a powerful reinforcement learning is a powerful technique, because it allows mission to learn from their experience, and also it makes the decisions in complex and uncertain situations also. It is similar to like how we can learn using trial and error method in the real world. So it's the same idea used in the reinforcement learning. Like here, there is a reward is there for the good choice, and punishment will be there for the bad choice. Okay, so reinforcement learning, it primarily relies on the feedback. That is what I told, experience feedback from the environment, rather than the labeled or unlabeled data. So your main goal is to learn the optimal behavior or strategy in a given environment first thing, and then decision making in dynamic environment, and it should handle the uncertainty situations also. And you can take a game playing, definitely it's an uncertainty situation will occur in game playing, and self-driving cars, and algorithmic trading to make decisions on buying or selling the financial instruments. These are the very important example applications which are designed using reinforcement learning. We have common algorithms.
Excuse me, sir.
Yes, sir.
Your PPT is not visible, sir.
Oh, 1 second, sir. 1 second. Sir, is it visible now?
No, sir. No, sir. No, visible, sir.
Visible now, sir?
Oh, yes, sir. Visible, sir.
Okay, thank you, sir. Thank you. Okay, the common algorithms for the reinforcement learning are Q-learning, deep Q networks, and policy gradient methods. Okay, in depth we are not discussing these things, but all these are the different types of the machine learning. Now we will move on to the next topic, that is deep learning. So we have completed artificial intelligence, machine intelligence, machine learning also completed. Now coming to the deep learning. What is deep learning? Deep learning is actually a subset of the machine learning. Okay, at its core, deep learning is based on the artificial neural network. It's a computational model, and this artificial neural network is inspired by the human brain, the structure and the functioning of the human brain. So a machine learning technique where computer can learn and make decisions by simulating the structure and function of the human brain through neural networks is called as a deep learning. So our human brain contains billions of neurons. Okay, and what is this neuron? Neuron is actually a small, most fundamental cell in the human brain. So human brain has many billions of neurons. So these neurons will interact and communicate with one another, and that will form the neural network actually. So working neural networks are what that enable the humans to think, and more importantly, learn. So the same concept is used in designing the artificial neural network and in deep learning also. If you see the architecture of an artificial neural network, architecture of ANN contains basically three layers. One is input layer, hidden layer, and output layer. So the input layer is like where the information goes into the artificial neural network, and it is a starting point of the ANN where the network receives the data, and the model needs to work on the data. And output layer is the one where the network gives the final result or the answer for the given problem. Okay, and it is the endpoint where the network tells us what it has learned or decided. Hidden layers comes in between input and output layer. These layers are in between the input and output layers, where the neurons in these layers process the information and help the network to learn the patterns and to make the decisions. This is the basic architecture of the ANN. Now, I'm going to explain now how this ANN works. Then we will consider the deep neural networks after understanding the working of ANN. Let me take one more example, a pandas example, to understand how a artificial neural network works. So here in this example, I have taken one image like panda, and assume there are 8 kids, 8 or 9 kids we have taken here. A number of kids are there. If the problem is to kid has to they have to identify the given image is panda or not. So now kid 1 to 6 have taken as the input, just like input layer. So for each kid we have given different parts of the panda, like as we know input layer, each kid will observe one aspect of the panda, like fur color or face shape. All these will form the input layer. And in the hidden layer, the kids pass their observations, what they have observed on the face of the panda or the color. Okay, we will pass these observations to each other, and mimicking the hidden layer. This exactly mimics the hidden layer of the neural network. And they will share the information also. When they collectively, they will build a model now. Collectively, they build a more comprehensive understanding of the panda future. So that you can observe in the kid 7, that is going to recognize the panda face, and kid 8 will recognize the panda's body. And these are the two hidden layers. And finally, in the output layer, recognition will happen. So the kid 9 will kid 9 will recognize the given image is a panda. So now they will come to the conclusion by combining all the details that it is a panda. Here, if the majority agrees that the observed characteristic matches with the panda, then the output will be panda. Otherwise, it is not a panda. So now, so here to identify the accuracy of the particular model, so we need to give a score for this. So to refine the if the given output is a panda, definitely we can give good score for that. If not, again we have to adjust the weights. So again, network is need to learn, and scoring approach will actually help us to adjust the network's parameters also to enhance accuracy over the time. So this is just one example I've taken to simulate the concept what I've explained in this example with the working of a artificial neural network. Now coming to deep neural networks. What is this deep neural network? A deep neural network, or DNN, is an artificial neural network with multiple layers. I've taken only one input, one output, and a hidden layer. So now we have multiple layers. So why the name deep here means? So deep means that it has multiple layers between input and output, and it makes it capable of learning complex patterns. If you want to learn more complex patterns, definitely this deep layer, more number of layers will help. And we have basically two types of deep learning models based on the requirement again, like discriminative model and generative model in the deep learning. And discriminative model is used to classify or predict the like given input, classification purpose or prediction purpose. If the model is designed, it's called a discriminative model. Or if you're generating something new, generating a new data that is similar to the data what I had given during the training, then it's called a generative model. Like for example, predicting a next word. While we are typing a message in using a smartphone, if the phone suggests some new word, next word, so there is a prediction. Okay, so it is generating new data using the training data. These are the two types of deep learning model. You can, in the diagram also you can observe like discriminative technique. There I have given dog as the input here, and the discriminative model will decide or label it as a dog. Okay, will classify it, label it as a dog. But in the generative model, will generate a dog image. I have given one dog image as the input. It generates this again one more dog image. Okay, or it may generate some text also. That is the generative model. It is a new content. Output will be in the generative model will be a new content. Now we will see the actual topic, the generative AI. So what is this generative AI? So we have covered, till now we have covered AI, ML, deep learning, and we have discussed two models also, discriminative and generative models. Now the generative AI is an artificial intelligence technology that can produce, that can generate various types of the content. The content may be like maybe text or image, or it may generate audio also, or it may generate a synthetic data like the data which looks like a real data. Okay, that is called synthetic data. So generative AI is a AI technique only. It is a AI technique which produces the various types of data. Now, what is generative AI? In short, it is called Gen AI, is a type of artificial intelligence that creates the new content based on what it has learned from the existing content. And how actually this new content is generated. The process of learning from the existing content is called as training, and that will be resulted in the designing of statistical model. When we give a prompt, and generative AI uses the statistical model to predict what an expected response might be, and this generates a new content. This is called as a generative AI. Now we will see where this generative AI will fit in the AI hierarchy. So this was the diagram I have used in the beginning of my presentation. Now the diagram is filled with all the different components. Like machine learning is having three types, and deep learning two models, and generative AI. And now in generative AI we have the components like transformer based language models, and generative adversarial networks, and variational autoencoders. So these are the different components of generative AI. So now we can define generative AI is a subset of deep learning. So this is the reason why we need to understand AI, ML, deep learning before understanding the generative AI. So this is a diagram. Will explain how actually the evaluation of AI with time. So now we are in the era of using generative AI. Started with AI, ML, and deep learning. Now it's generative AI. And generative AI have two types of generative models. Like generative AI uses different types of machine learning models called generative models. The generative models main function is to learns the underlying set of data, and it will generate the new data that closely matches with the original data. And these generative models are mainly used to create new content like images it may generate, or text, or even music also it can generate. And these generative models uses the unsupervised learning approach. Now we will see the generative models, two types of generative models. One is the generative language models, and another one is generative image models. Generative language models learn about the patterns in a given language through training data. So then, given some text, they may predict what comes next. That is called as a generative language model. If I consider generative image model, the generative image models produce new images using a technique called diffusion. And here, a given prompt or a related image will transform the random noise into images, or it will generate the images from the prompts. So these are the two generative models, like one is generative language model and another is generative image model. Now, based on the type input, we have types of generative AI. If the AI input, generative AI input data type is image, then we have the outputs like text, from image to text. Under that, we have the applications like image captioning, visual question answering, or image search is there, that we have we are using now image search also. And one more, image to image, input is image, output is also image, like super resolution, image completion, and image to video is also there, like output will be video like animations. This is one type of generative AI. It is based on the input image. And the next one is based on the input to text. Input type is text here. So text to text, input is also text, output is also text, like the applications like translation from one language to another language, summarization, question answering, grammar correction. All these are the applications where the input is text and output is also text. And text to image, where we have image generation like video generation, and text to audio, that is text to speech application, and output text to decisions also there, like while we are playing the games, like decisions should happen. Okay, so these are the applications comes under the next model of Gen AI, that is where the input is text. Now I want to, in the next slides, I want to explain by taking one application of generative AI, okay, and how all these models are deployed in designing that application. That is ChatGPT. Okay, that this ChatGPT is an application. As we know, ChatGPT is a chatbot designed using like a ChatGPT is a generative AI application. Okay, designed using the large language models. It's a large language model based chatbot, and ChatGPT means it's a generative pre-trained transformer. Okay, a generative AI system which needs to generate the human-like text, which requires large language models. Here, the generative means it creates the text responses, means it generates the text responses for the given text input. And pre-trained means it uses billions of text files to respond. And transformer means a machine learning model that determines the possible outputs based on the probability. So that's why it's called as a ChatGPT. And now we will see how this ChatGPT works, how generative AI works in the next slide. So here, these 6 steps will explain how actually generative AI works. Step 1, like user inputs a prompt or a question into the ChatGPT. For example, there is a statement like write a 150-word essay on the Impressionism movement in 19th century France and its characteristics. This is the prompt message I had given at the ChatGPT. Is step 1. Step 2, what will happen? ChatGPT uses the deep learning algorithm to analyze the prompt and it will generate the response. In the step 3, ChatGPT identifies the keywords and phrases in the prompt to understand the context of the question. For example, in this question, there is a command called write an essay in 150 words is a command. On which topic? Topic is also identified. There is Impressionism characteristics, 19th century France. So now moving on to the step 4, ChatGPT will access its database of information to find the relevant information related to the prompt. And what does it know about writing essays, or what does it know about the time, country, and characteristics of this artistic movement? Everything will be collected in step 4. In step 5, ChatGPT uses the natural language processing techniques to generate the responses, and that is grammatically correct and contextually relevant. The output will be generated, and that in the step 6, ChatGPT presents the response to the user, and the user who can continue with that input, with that output, or he may provide additional prompts also to get the more refined or relevant output from the ChatGPT. This is how the generative AI works. Now, basically, what this generative AI requires to give this output, a text output, or to generate the text, it requires language model is a type of machine learning model which uses the various statistical and probabilistic techniques to generate the text. And am I audible?
Audible, sir.
Audible, sir.
Okay. Some noise is coming. That's why I asked. Okay, thank you. So when we use messaging apps in our phone, I think we have
PPT.
observed. Hello.
Hello, sir. PPT is not visible, sir.
Okay, 1 second.
Yeah, now it's visible, sir.
Visible, sir. Hello, sir.
I'm very sorry. Sir, is it audible, sir, now?
Oh, audible, sir. Audible, sir.
PPT is presenting, no? Fine?
Yes, sir. Yes, sir.
Okay, thank you. Okay, so we'll take one example for the language model. Like if we type a message like I am going to in our phone, it will predict the next word, like whether I'm going to store or park or office, like that. Okay. So because these are the usually the regular words we will use in everyday language. So this prediction is made based on on the context of what we have typed so far and the patterns it has learned from the analyzing of lots of text. This is called as a language model, where this is the very important part for the chat GPT. Now coming to the large language model, where the large language model is a language model which is a type of machine learning model that is trained on a large data set of the text, and it uses the advanced neural network architectures to generate the prediction or to generate the any text or to predict some like a human. So if you see the where and all the application large language models are required, we have the applications like virtual assistants, chatbots, language translation, or text generation, summarization, or sentiment analysis. You take any of these applications, the large language models are used for this. And it's a, as I already told you, it's a type of deep learning model. It's trained on the large data set of text, and it is uses the advanced neural network architectures. And many applications are there where the large language models are used. Now we will see how these large language models are used and where and all these large language models are used. As I already mentioned in the previous diagram, the first application like virtual assistants, the large language models are the actual engines that gives the power to the virtual assistants. For example, Siri, Alexa, or Google Assistant. We have already experienced with this. So actual power for this virtual assistant is given by the large language models. So that analyze the human command. What is the command we had given for the virtual assistant, and it will interpret the meaning out of it, and helping these virtual assistants to perform the several actions on users on behalf of the user. So there the large language model is used. And the second application like chatbots or ChatGPT is not a new word anymore. Okay, and most of us have used it or similar AI conversational chatbots we have used. And these chatbots uses the LLM to understand the human questions and response in a way like a human is responding. And the next application is like language translation. We know a Google Translator. It also uses the large language model, and these models are trained on a huge amount of multilingual text data, which enable to capture the subtle distinctions or variations or context and even complexity of different languages. When we ask the translator to translate the sentence, it uses the LLM algorithm to analyze the input text in one language and generate an accurate and contextually appropriate translation in the target language. So by considering the relationships between the words and the phrases in both the languages bidirectionally, LLM can produce a translations that preserve the actual meaning and the tone of the original text. Now we'll move on to the next application called is the text generation. And obviously LLM models can be used to compose the stories also and generating product descriptions. And even nowadays you can use LLM models to write the emails, and even we have seen in WhatsApp Meta is also it's using LLM model. And even summarization, definitely you can use we have seen these applications also. Even if you give one page of our biodata now.
Sir, your screen is not visible, sir.
Sorry, sir. One second.
Sir, now it's shared, sir.
Sir, is it visible now?
Yes, sir.
Okay, maybe network issue. Okay, right. Okay. The next application where the LLMs are used, like sentiment analysis, as we know, the main objective is to determine the sentiment or emotion which is expressed in the given text. LLM models can be used here to analyze the huge amounts of the text data, understand the context, and also tone of the language. If it is a speech, tone of the language, and identify the sentiment polarity, like whether it is a positive sentiment or negative or neutral, where again LLM is required. And we know one more application like content recommendations. As I have already mentioned in the real applications of real world applications of AI, Netflix, YouTube, or Amazon, any shopping website where we know these content recommendations, where there also LLMs are used. Now, this generative AI works based on LLM, and missions are also learning. And what we need to learn to use these generative AIs effectively, obviously, that is a prompt. So, prompt engineering is the most demanding one. Missions are learning now, but we also need to learn how to interact with the mission. So this can happen through by giving the right or correct prompts as an input for the generative AI. Prompts are nothing but a very simple, are the inputs or questions user gives to AI systems to get a specific response. And how these prompts can be designed is the very interesting thing or very important thing. So these prompts can be a sentences in a plain English or even any other human language also, because ChatGPT is available for other languages also, not only for English. And prompts can be it may be a code snippets also, or it may be commands or any other combination of text and code also. Let me take two examples. This is the one screenshot where we can see we have given the one input like one prompt like tell me a story which includes animal characters. The story is targeted for kids. If I give this prompt, it will generate the story where the animal characters are there, and that story targeted for the kids. This is one way of giving the prompt. And if you see in the next slide, you can observe here. There we have given, there's a screenshot of DAL-E web page. See, this DAL-E web page is actually a generative AI where it will generate the images. Okay, so here the prompt, we have given the prompt like an astronaut riding a horse in photorealistic style. Okay, and that is the prompt given, and this generative AI has designed a beautiful image like this. Okay, so it purely depends on how actually you are giving the prompt. So based on prompt only, we will get the correct response. Now we will see how to use this prompt engineering to get the better results. So the three important concepts in prompt engineering we should follow. One is the specificity, and contextualization and fine tuning. So what is the specificity? While you are designing the prompt, while you are giving the prompt, it should be like very specific related to a particular problem, or your prompt should be very specific to that problem. For example, like if I give a prompt like tell me about cars, it is not a specific prompt. You can redefine it like can you describe the features of electric cars compared to traditional gasoline cars? It is a right specific prompt. Clearly, you have mentioned the types of cars also here. This is one method of giving the correct prompt for the generative AI. And being specific, it helps the AI to understand exactly what you are asking for, and so it can give a better answer to the user. And coming to the Sir, is my presentation is visible?
Yes, sir.
Okay.
It's visible, sir.
Okay. Next one is contextualization. In contextualization, prompt engineering, giving a AI model a clear details and
Sir,
information.
PPT is not visible, sir.
Just now it has gone, PPT. It's
Now
visible,
visible,
sir,
sir.
now.
Give me 1 minute. Just I'm changing this data to Wi-Fi to my mobile data. Once. Okay. Sorry for the inconvenience. Okay. I think it's visible now. So in
Yes,
the
sir.
contextualization, as I already mentioned, we give the AI model a clear details and information about the situation or task it is being asked to do. That context we should provide. For example, write a review of this product is a non-contextualized prompt. Instead of that, you give a prompt like write a review of this product focusing on its performance for outdoor activities. There is a clear complete environment or the context is defined in this prompt. This is what it is similar to providing a background story or setting the sentence for the AI. So this will help the AI system to understand what it is supposed to do and who it is supposed to do it for. Okay, that is what the contextualization. And one more to get the better results, what we need to follow is the fine tuning. Instead of writing a prompt like write a story about a dog, if you write a heartwarming story about a golden retriever named Max who helps a little girl overcome her fear of swimming. So there is you will get a complete one story, beautiful story about that situation. So hence why fine tuning is a one more process of a trial and error method. We keep on designing the prompt. Okay, we will get a better until you get a better response. You keep on changing the prompt. We'll refine the prompt, and you will get a better result also. So these are the three things we should follow while designing the prompt. And now we'll see how to write the effective prompts. What are the things we should follow while writing the effective prompts? There are important points we should follow in writing the effective prompts. First one is the be clear and specific. So be clear and specific. And the second one is the provide context. Use examples. Means your prompt should be very clear and specific prompt, and provide the context in which context you are asking you are sending the question to the generative AI, and even you can use the examples also while writing the prompts. And if you want to ask any questions, ask the specific questions. And even sometimes in questions we need to specify the constraints also, include the constraints, or as I mentioned, fine tuning or test and iterate, like a trial and error method in designing the prompts. These are the methods we can follow in writing the effective prompts. So now we will see what are the ethical considerations or the challenges with generative AI. So is generative AI, whatever the input it is giving, ethically right, or using generative AI is ethically right or wrong? What are the problems we may face? What are the challenges we need to face when we are using generative AI? So like generative AI, as we know, can achieve a remarkable task like support, even medical field also we can use generative AI like to discover the drug or cancer diagnosis, or even you can use it for the creating to create a beautiful artwork or videos or images or even music also. But with the enormous applications of generative AI, there is a due to lack of regulations. There are many ways it can be misused as well. Like other forms of AI, generative AI can cause a number of ethical issues and risks surrounding the data privacy, security, policies, and workforces. Under that, the very first one is the copyright and the data theft issues. Obviously, because this generative AI or the chat GPT will give the responses based on the huge amount of database. Okay, based on the database only, it will give the responses. Whenever the generative AI can generate the content, like such as images, music, or text, that closely resembles the copyrighted material, right? Because it will take the content from the existing database only. If this generated content is distributed or used without permission, definitely it could infringe on the original creators of the copyright. This is one of the big issue we need to follow while using the generative AI. And the second one is the plagiarism. And the content generated by AI could be used to plagiarize the existing works also, such as academic papers that we are observing now in the even nowadays the plagiarism softwares are displaying the generative AI chat GPT content also, like this is the content taken from the generative AI or the chat GPT. So because this is very important, otherwise even content what we have received from the chat GPT can't be considered as our original work. Okay, so if AI generated content is passed off as original work without proper attribution, it can lead to copyright infringement and academic dishonesty. And the third problem or the challenge will be definitely data reuse and replication. And in the data reuse and replication, like the test generators trained on private logs or medical records, if based on these medical records or the private chat logs, if it is trained, definitely that could produce some sensitive information also as output. When this sensitive information is released, definitely that will lead to the data breaches or and even privacy violations also. This is one more challenge or ethical considerations we should. These are the challenges where we need to work on chat GPT to overcome from these challenges. And the next one is like we have another one like forgery and fraud and reverse engineering also. Like forgery and fraud will also comes under the same copyright and data theft issues only. And reverse engineering, like with the input by considering the chat GPT output, by doing the reverse engineering, we can build the original one. Again, we can't claim this as a the work of ours. Okay, so that is again a copyright issue only. Coming to the next part, like what are the ethical in the ethical consideration of the challenges? Like one more is the harmful content distribution. Definitely, it is one more problem. Like maybe the content what we have received from the generative AI, maybe the harmful content also that can't be distributed to everywhere. And creation of a fake content, like generative AI algorithms can produce a very highly realistic fake images or videos and even audio text also. But these creations can be used to spread the misinformation to the outside world. That is one more problem. And even nowadays, there is a big issue what we are observing, deep fakes. There is a deep fake is a technology. It is a specific application of generative AI only that allows for the manipulation of the audio-visual content to make it looks like someone said or did something they didn't. This can be used maliciously to create fake videos of public figures or celebrities. Even our ordinary people engaging in inappropriate or harmful behavior. This is the one big issue what we are facing now, deep fakes. And even the next one is the automated content generation. The generative AI can automatically create a large volumes of content that we have observed also. And like spam mails or fake reviews or malicious messages. Okay, these are the examples for the automated content generation. And this can overwhelm the online platforms and communities with low quality or harmful content, and that will make difficult to distinguish between which one is the genuine or which one is fake information. So these are the main big challenges what we are facing with respect to the output of the generative AI. Ethical challenges what we are facing. And next, coming to the challenges and limitations. Is there any challenges are there for the or the limitations are there in generative AI? Of course, it's there definitely. Like one is the with high level generative AI, it looks like an absolutely game changer nowadays. But it also has the limitations. Like in reality, there are still some major challenges and limitations are there which needs to be solved. Here we can work on the next work. If anybody want to work on these issues, it's really a open-ended problem. Like one is the training time, like intensive resource requirements for training generative AI models requires the training time. The training time will be more since generative AI models are trained on huge data set. Definitely, it requires more time. Okay, near the efficient training algorithms. Okay, next coming to the hardware requirements, definitely high performance CPUs and GPUs or memories are required here. So other than any other hardware components, these things are required. And energy consumption is also more here. Like it consumes a significant amount of energy, which also leads to environmental concerns, particularly the carbon emissions. These are the some limitations are there with respect to generative AI. It cannot altogether start a new type of storytelling techniques or start a new generation of music. Maybe like with all these limitations and challenges, if you work on the generative AI, definitely there is a scope for the next coming research also. We can take all these challenges or limitations as one more the next problems where we can work. And one more area or the what I can suggest here is like if we design large language models for the regional languages, like as we know, very less amount of work happened for the Indian languages compared to other languages. So there is a large scope of research scope is there on regional languages. So at least we can build some language models for the regional languages, and that is going to be definitely there is going to be a very big contribution for our regional languages or Indian languages. So much of work is happening. That's why NLP is rocking now. So like basically natural language processing and these deep learning models are the very trending areas. Will give more open-ended problem for the research community also. So with these challenges, I would like to recap what we have learned so far. I started my presentation with the question like what is the technology innovation what we are observing, and the answer was ChatGPT or the generative AI. Then I have explained the AI, artificial intelligence, like with a simple analogy. We will recap all this what we have learned now. with a simple example I have taken, and we have learned the capabilities of AI and how it is changing our day-to-day life, and different types of AI with examples. We have also understood how AI is different from human intelligence. Then I have taken machine learning, types of learning also we have discussed. Coming to deep learning, we have learned how deep learning is inspired from human brain, and we understood how artificial neural network works with a pandas example. And we learned how deep learning is used to solve complicated problems. And then I have connected this with the generative AI, with the two models of deep learning, like discriminative model and the generative model. And in the generative AI, with a simple analogy example, we have learned the generative AIs, and we understood how generative AI is different from the AI also. And then I have taken large language model with why the language model is required for the generative AI. Okay. And then I've discussed about the prompt engineering. In the prompt engineering, we have learned what prompt and how prompt can be designed, how we can design a correct prompt also. And in the last slide, we have discussed about the ethical challenges and the limitations of generative AI. So with this, I would like to conclude my talk on generative AI. So generative AI is very demanding, required. A lot of scope is there, but always all technology, any new technology will be released to the market with some challenges only. So definitely we can overcome from these challenges also. And even nowadays there is a big threat is there at the industry side also, like with respect to the job also, like if chat GPT or generative AI is doing all the work, then there will be a chance of it can replace the even the industry software engineers also. That scarcity is there, but still what we can say, human intelligence is bigger than the machine intelligence. So with this, I would like to conclude my topic. I thank the management for providing an opportunity to deliver a talk on introduction to generative AI. And maybe the coming speaker or the resource person of the tomorrow's resource person will discuss in more detail about the technology aspects, like how mathematics can be used in building these models. Okay, that will be delivered by our beloved principal sir in tomorrow's session. Yeah, if you have any, definitely if you have any questions, you can ask. Yeah, 1 second. Is one question. There is one question. Let me do. What is the question, sir? Kindly show how to do directly in Chat GPT. Which one you are asking? I don't know. There was a question. Like kindly show how to do this directly in Chat GPT. No, I think maybe this question was related to maybe the image generation, I think. Yeah, for that we have our Chat GPT. Maybe that application won't work. For that we have DAL-E and or even you can use image generator also. Image generator, generative AI. And any other questions? I think no more questions. If you have any questions, definitely you can communicate with me, like in my mail ID manjunathabh@sjcat.ac.in. I will type my mail ID here in the chat box. If you have any questions, please let me know the questions. Manjunatha BH at sjcit.ac.in. Chart explain again, please.
Thank you so much, sir. On behalf of everyone here, I would like to sincerely thank you for today's session. And your insights and expertise has been incredibly valuable. And we are very grateful for the time and effort you are putting here and sharing your knowledge with us. Thank you so much, sir.
Thank you, madam. Thank you. Thank you, Kiran sir, Ajay sir, and Shweta madam, Aishwarya madam.
Thank you, sir.
Thank you, sir. Thank you, sir.
Thank you, sir.
Thank you. The next sessions will be starting within 5 minutes. So within 5 minutes, we can start the next session. So meanwhile, if any participants have any doubts, you can post in the chat. As the next resource person needs to join. So hope you understand. Thank you.
Sorry, sir.
Ajay, shall I leave the meeting?
Yes, sir. Yes, sir. Yes, sir.
Thank you.
Thank you, sir.
So thank you, sir.
Shweta madam.
Hello.
Shweta madam.
Sir, tell sir.
Resource person joined madam.
Okay, sir. Aishwarya ma'am.
Yes, ma'am.
Okay, ma'am, you proceed.
Yeah. I welcome you all back. So as we are beginning with the session 8 on AI and large language models by Dr. Tamme Gowda. So before that, I request Ms. Gayatri to introduce our resource person. Over to you, ma'am. Gayatri, ma'am.
Jai Shri Gurudev. Myself Gayatri, working as an assistant professor, Department of CSE. It's my honor to introduce our speaker, Dr. Tamme Gowda. Sir is a senior research and scientist at Microsoft in Raymond, Washington. Sir earned his bachelor's degree in computer science and engineering from SJCIT, followed by a master's degree and PhD both in computer science from the University of South, South California, Los Angeles. Sir begins his professional journey in Bangalore as a software engineer. After moving to California in 2015 from his graduate students, Sir worked as a data scientist intern at NASA Jet Professional Laboratory and as a research engineer at USC Information Science and Institute. In addition to his professional work, Sir has also served as a project management committee member at the Apache Software Foundation, mentored students at Google Summary of Code, and is one of the organizers of workshop on mission translation. Sir also published papers at top tier conferences and proud to say that Sir is our alumni of SJCAT. Thank you everyone. Now I request you to take over, sir. Thank you, sir.
Thank you, ma'am, for the intro. Hi, everybody. Can you hear me?
Yeah, it's audible, sir.
Oh, okay, perfect. Good evening. I'm in the Redmond, Washington. It's still dark, 6 a.m. For me, sunrise will be at 8. All right, I think we have 1.5 hours for this talk. I have some slides. Let's begin with testing if our screen share works. I'm going to, let me see if I can share my slides. Present. Sorry, give me one moment. Slideshow, present from beginning. So I'm sharing my screen. Can somebody confirm if you can see my screen?
Yeah, it's visible, sir.
Okay, and it's in the full screen mode. Awesome. Okay. Awesome. Okay, let's get started. So for the next hour or so, we'll be talking about large language models. Thank you for the intro. Happy to be here. Let's get started. So you probably have been hearing a lot in the news about large language models. Something like ChatGPT, for instance, and Gemini from Google, ChatGPT from OpenAI, Claude from Anthropic, Llama from Meta/Facebook, Grok from X/Twitter, Pi from Microsoft. So there are so many of these going on in the news. In fact, every day you wake up for a new announcement these days. This 1 hour or so is going to be about what are these and how are these built, and are there some interesting topics that we can pursue for research, right? So more specifically, just a few specific topics we're going to touch. So as the topic says, it's large language models, but before we get to large part, we start with just a regular language model. What does it mean? How do we train? How to run inference? So sorry, let me confirm. Are you all able to see my screen now with the overview? Because sometimes the screen sharing might stop working. Can somebody confirm if you are able to see my screen that says overview, or is it?
Is it visible, sir?
Okay, awesome. Thank you. Let me know if the slides stop advancing. Please let me know. All right. So first, we spend some time learning about language models. Specifically, how do we train them, and how to run some inference on the language models. Then we move on to the large language models part. So as you can imagine, large language model didn't come out of the blue, right? There has been decades of work going on, just that something happened in the past few years, and now it's hot news, but something happened. So what exactly happened? So that we will study with the case study on ChatGPT. I think ChatGPT is the one that triggered a lot of new exciting development in the area. Then we discuss, can ChatGPT solve everything? When I say ChatGPT, all those large language models I showed you in the beginning, just using ChatGPT as a specific example, but it will apply to all the language models. Can they solve all the problems? Well, spoiler alert, they can't solve all the problems, and there will be cases where they're not good and you have to do something extra to solve some new problem. And we're going to discuss how do we do that. Specifically, you may have heard terms like prompting and instructions. And in the end, we talk about evaluation. Also, I had shared these slides a couple of weeks ago. They were pretty outdated, so I will send the new slides once this talk finish. All right. So the next slide. All right, so let's start with the language model, or LM in short. So what are language models? So probably heard, most of you are familiar, heard of this. This is a model for predicting probability of sequences. So when you think of language model, think of sequences. Sequences is a very generic term. Sometimes language modeling is also called sequence modeling. Any specific sequence, for instance, all the natural languages are sequences. So think of, for instance, these are the words in your favorite language, Kannada, English, Hindi, you name it. So the language models, the goal here is modeling the probability of the sequence. Okay, so you might see terms like probability of X subscript 1 colon n. It means sequence from 1 to n, and you can expand it as terms x1, x2, x3, xn. Then how do we model this probability? So this is standard textbook definition. If you look inside natural language processing or language models, so you see you can decompose this into a few terms, like starting with probability of just the first term. What is the probability of you seeing the first term? And then second term given the first one, third term given the so far first two, and so on. And in the end, the probability of the last term given everything before this. So as you can see the pattern, so more generally probability of xi given everything before that. That includes sequence from starting from term 1 to everything before I, which is I minus 1. And we multiply these probabilities. So when you see some research paper, you might see instead of multiplication, you would see summation and logarithm. Well, another one practical problem. This is how we define it in theory, but in practice, when you multiply too many numbers, especially if they are between 0 to 1, you will see some floating point underflow. So we use logarithms and sum them. So don't be surprised if you see summation of log probabilities. It's the same, but practically logarithms are used for numerical stability. Okay, so in summary, so if this math is a bit confusing in natural language definition, so for any given prefix, so this model can predict a next token. So I specifically highlight a next token instead of the, because there can be many possibilities. We just have to predict one of those many. So this seems very basic, but don't be surprised. This can solve a lot of problems. There has been debate whether this is powerful enough to solve all the problems that we see in our day-to-day life. Some argue for yes, this can solve everything. Others say no, it cannot solve everything. Especially say, can this yield to artificial intelligence? It's a simple equation, predict the next thing given everything it has seen before. Well, this is the core of all the large language models. And if you are seeing LLMs doing pretty amazing things, all because of this equation. So it can solve a lot of problems. I would like to highlight two kind of problems. First one is completion. This is very popular. I think it's just rephrasing what I just told. Given a prefix, the model has to complete a possible suffix. So if you pick one best answer at every step, you get one possible option. You can also sample from it. By sampling, we mean not necessarily you pick the top probability. You can pick, say, something in the top 5, and then you end up getting completely different suffix. But majority of them will be usable or are good enough completion. So the terms prefix, so these days we start hearing them as prompt, and the suffix, we hear it as completion. So that is just the first kind of problem. So if you see LLMs, you ask something and then it gives you an amazing answer. So the question you asked is the prefix, and the answer it gives you is suffix. And then the second kind of problem, or ranking problem, very related to completion, but slightly different, which is if you give a set of sequences. So in this case, let's say I give you a multiple choice question. The LLM doesn't have to produce an answer, but it has 4 possibilities. A typical exam I had when I was a student at SGCIT, sometimes you get a question and ABCD, 4 choices. Now LLM has to rank which one is more likely, what is the most probable sequence. It's slightly different, like asking a question and ask you to write an answer for 5 marks versus here is a multiple choice question, what is the correct answer, right? So all the underlying, the equation is same, probability xi given everything before xi, but how we use it is either you sample a token and run a for loop on it, that's a completion, or you force the model to give you a probability by multiplying all the terms and then see which one is more likely. So there's 2 kinds of problems. Then the next step is, let's talk about LLM training. So as we discussed, LLMs are just probabilistic models. That means we are modeling probabilities, right? The output of probabilities 0 to 1, a quick refresher, or probably I think that it will be covered in the upcoming talks. Input to this model is a sequence. Output is a probability. So what exactly is a probability? So in this case, it gives you a vector. P of xi, it's not a single number in this case. It gives you a vector of probabilities where the vector size v is the vocabulary or number of classes in your model, such that they sum to 1, right? So that's our goal. And how do we learn such things? So here, more concretely, we have a function whose outputs are within the range 0 to 1, and it has to produce a vector. How do we learn such functions? So the answer is machine learning, right? So, but historically, there are different family of, there are many approaches in machine learning. Historically, up to, I think, 5 years ago or so, we were relying, maybe 10 years, now it's 2025, we were relying heavily on n-gram models. So there are 2 family of machine learning approaches. One is a parametric model, other one is a non-parametric. So So n-gram models, you may have heard like bigram, trigram, 4-gram, 5-gram models. These are non-parametric models. And then now the parametric models like deep learning. So we learn this function by parameterizing this as a set of theta as a set of parameters. And we learn the theta from a set of examples. So we take training examples and learn a bunch of parameters. And this function, learned function, approximates what we want. So that's the core idea of machine learning, right? And within machine learning, again, there are so many approaches. The current approach is neural network / deep learning. And within deep learning, there are so many, again, approaches, so many kinds of neural networks. We used to use recurrent neural networks, the terms you may have heard, LSTM, or long short-term memory networks, or GRU. Right now, we are in the era of transformers, which we will talk more. I mentioned we learn these from a set of examples. How does those set of examples look like? You might be wondering. So this set of examples, what we call training data, is just a set of natural language sentences. Like imagine you have a book and you extract all the sentences in it, that's your training data. Imagine you have some news articles, go to your favorite newspaper, there are a bunch of articles, you extract them, that's your training data. Web pages, so anything you see on the web, and you crawl it, extract it, that's your training data. So as you see, for some problems, it's difficult to get training data. For instance, think of, say, standard examples you may have seen in a machine learning book, say cancer detection. So you have to have images, and then somebody has to sit and label them as this is cancer and this is not cancer. And you need a trained professional like a doctor to look at these images and give them labels. Whereas language models, it's very relatively easy to get training data. You just have to crawl web, and there is no extra annotation. Just assume the text is written by somebody who knows how to write in that language. That's it. So training data is relatively easy to get. Next step, we are moving on to language models with deep learning. So as we mentioned, transformers are a new approach. So let's spend a little bit more time in learning how to do this in deep learning. One moment. All right, so as we saw in the previous slide, given a sequence, we need to model probability. And with deep learning, one point I would like to highlight is, so the core philosophy of deep learning here is you have input, you have output, everything end to end in one single optimized network. So that's the core philosophy of deep learning. But before these neural networks, we might break it down into multiple steps. We would optimize them separately and then put them together and expect it. Everything works as one big application. For instance, think of it like how we assemble cars. We make parts separately and then we put them together and then expect the car as a whole works. Whereas the idea of deep learning is all the parts are simultaneously assembled and optimized to make it work with each other. So that's the end-to-end optimization network part. But the thing I want to highlight here is deep learning. You have heard with terms like backpropagation, differentiability, functions. So basically, these are continuous vector machines. In a sense, they work with continuous data. But natural language is discrete. Think of them as categorical variables, if you remember our probability theory. So what exactly do I mean by this? So imagine you have you're predicting temperature or a house price or speed. So you are off by, suppose you were supposed to predict temperature 20, but you are off by only 119. So it's not too bad. Whereas here, in terms of discrete, there is no order in between your items you're predicting. So you were supposed to predict the word the, but you predicted the word off. It's as bad as anything else, right? So whereas in continuous word, you're only off by 1 unit, so no big deal. So here we're dealing with words. So this can be a bit problematic. So let me summarize it that way. But we have a way of handling this. So what do we do? So at high level, the problem I'm trying to describe is the data that we're dealing with are categorical random variables. In a sense, if you predict wrong thing, it's wrong. You can't say, oh, you're only off by just 1 unit. But the inside deep learning, everything works in a continuous space, so we have to map them. So the steps we do is we have input mapping. So all the words in a natural language that we see, example, the word like the in English, we need to map it to a real valued vector. And how do we accomplish that? So we have, the first step is we learn something called vocabulary, where it maps every symbol into an integer. So every time you see a word the in your input, we have an integer, or it is an index in a table. So it gets mapped to some number, say 20 or 30, some number. As long as it's consistent during training and inference, we are good. Then we use another thing, construct called embedding metrics. So this has a stack of vectors. When the first part, vocabulary, gives word to the index, and this we just look up that specific row in the matrix, and that is our embedding vector, or what we call word embedding. So so that's how we solve the input side of the problem, which is, so we see all the symbols in the input, or the two words in the input, and then we look them up in the embedding matrix, and then we get a vector that is a continuous or real valued vector. And everything else inside the model are vectors, real valued vectors to be specific. We also do something like we add some special tokens initially, like beginning of the sequence, in the end of the sequence. Then all of them are embeddings. Embeddings basically means real valued vector. Then the next step is a deep learning model. So think of them at high level as transforming these embeddings. So they map one vectors from one space to other space. How exactly do that depends on the models we are going to, some of them we are going to briefly touch. Started from inputs, we map them to real valued space, then think of some deep learning model that transforms these vector within, depending on the task we're doing, and then output mapping. So now we have to bring that real valued vector back to the symbolic word or the categorical word. How do we do that? So we take that embedding, and then we've mentioned the embedding matrix, where we have a V number of vectors. We go and compute dot product with every one of those vectors. And then we see which one has a better similarity. And that gives us, then we normalize them to 0 to 1. So there is this function called softmax, which helps us normalize arbitrary real numbers to a probability vector. So we compute dot product with the vectors, and then the one that is very close to it will give a higher value, and then we normalize them to 0 to 1. That will have a highest probability, and then we pick that symbol. So this is how the input and output transformation is done. Then let's spend a bit more time on the vocabulary or tokenization part. So as many of us know, natural languages have follow Zipf's law, which means a few words have a lot of tokens, but a lot of word types are very rare. You only have one, you only see them one time, or maybe you don't see them at all in your training data. So in English, for instance, the most popular word, or the word type that has the most number of tokens in any English training data set is going to be, let's see if somebody can answer. Can you all still hear me?
Yeah, it's audible, sir.
Okay. Yeah, so the most popular word in English is, when you look at your training data, you see the word the occurring a lot of times. But then when you look at the names of people, say everybody in this audience, and then you look at your name on any training data, well, you are lucky if your name is there once. A lot of us, our names don't even appear in our training data at all. then that will have a consequence on how we learn probabilities. Because if the model doesn't see this word, then how do we even model that word? Right? This was a huge problem for a long time, and there were so many approaches we were trying to solve, but we're not going to get into all the details. But just want to highlight how do we actually solve this with language models. Since 2016, what we do is, given any word, we have a way of splitting that words into pieces. One popular approach is byte pair encoding, which was introduced in 2016. So we have a hyperparameter that can control how to segment these words. So if you see, let's say you input your name and your name is not part of training data, then we start looking at the pieces in your name. Worst case scenario, your name might be split into pieces like characters, and characters are going to be in vocabulary. Byte pair encoding, for some lucky words, you might have it as full, some of them you might have it as a bunch of pieces. For a lot of the rare words or unique words, you might see them as sequence of characters, right? So this is one of the fascinating idea when I was working in a PhD. But the recent works is now we can actually train models at character sequences. You don't even have to look at words as a whole. And there's been even recent works like the Unicode characters. If you're working in multilingual models, like if your model has to support all popular languages, including Indian languages, so you might just look at the Unicode code points as your vocabulary. Then even fairly recently, we are also looking at some models that can work with bytes. So I guess the message I'm trying to say is the words doesn't have to be really words. The input doesn't have to be some meaningful words. We can split them, butcher them into pieces, input them as characters, bytes. These models the new models are so amazing, they can still handle. So don't be surprised at some point you see, okay, now we are going to feed an image as pixels. Or now we are going to feed an audio wave. So because they don't have to be words at all. So for the audience, something to think about, what happens, how does these models handle Indian languages? Let's say you have some words written in Hindi or Kannada or Telugu, whatever your favorite language is. So how does it handle words in our languages? So a lot of the times these models split them into too many pieces and the sequences get longer. And this is one of the active area of research where some of the language models don't do well for Indian languages, and we're trying to address them. Okay, so I promised you at a high level, we'll take a look at the neural networks. Again, we could spend a whole hour just discussing one of these models, but I would try to be as high level as possible. So in the previous slide, I mentioned at high level, think of all neural networks as vector transforming machines. We have some input vector, they do some magic and give you an output vector, right? So then you would hear something like feed-forward network. One very simple neural network is feed-forward network. I think if you look into neural networks, that's the place where we start. But those are too simple for this problem. So here the problem we have is we have sequence of input, and there is dependency between the words or tokens in the sequence. Right? If you look at the sentence, any sentence, the cat sat, the typical example people use, the cat sat on a mat, and the words have dependency between them. So there is grammar, there is syntax, there is semantics, so you can't process them independently. And for this class of problems, what we call sequence modeling, where everything in the sequence has dependency across, we use this class of neural network we used to use this class of neural network called recurrent neural networks. Proposed way early, there was a simple recurrent neural network, and then the three I list here are LSTM, GRU, SRU. These are fairly recent. For instance, LSTM itself dates back to 1995. So the core idea here is, so as you see in the image, there is more like a loop. Then we unfold the loop. So every time you have an input, the model updates its hidden state, produces an output, and then there is a next time when you have an input, it reuses the state from previous computation. So the state that is ht-1 is reused to compute or update, is updated to obtain ht. So this is how it handles the sequential dependency. As you see, every time it's doing something, some transformation of the input, it reuses the states, previous state, and the previous state handles the dependencies. So this class of network, recurrent neural networks, the popular one was long short-term memory network. We used it until maybe it's still used. GRU, gated recurrent unit, SRU, simpler recurrent unit. Some of them are still used. But then there is another class of neural network, convolutional neural networks, or CNNs, which are used for images. At least we used to use them until transformers, which are until 2020 or so. These are popular for images, handling images. But for a brief moment in history, we use them for language model also. But around the same time, transformers, a new kind of network announced in 2017. And now it is popular for everything. So maybe I'll give you a high-level overview of transformers, because this is the one we are currently using. So before we get into transformers alone, just take a look at it from the top bird's eye view of neural networks. So initially, we were using encoder-decoder networks. So if you come across some research works or blog posts that talk about encoder-decoder networks, what exactly are we doing? So we had a pair of neural networks. One is called encoder, other one is a decoder neural network. Encoder encodes the input. It means what's different between encoder and decoder is encoder is bidirectional. It means it can look at the whole sequence, both left and right, both past and future, because the input, it's all available. Decoder is unidirectional. It can only go from left to right. So decoder generates the output. It cannot look into the future that it hasn't generated yet. But encoder can look into the future because it's input, it's already available. So there is a slight difference between how these are implemented, but at a high level, our NLP models were based on a pair of networks, encoder and decoder. Then we forked encoder separately. There was a line of work explored encoder, especially if you just want to understand the input, you don't worry about producing the new outputs, then encoder is also go-to place. Then decoder, if you want to understand as well as produce some outputs. OpenAI's GPT model started this decoder-only models, pre-trained models. I think GPT generative pre-trained transformers, and now almost everybody is focusing on decoder-only models. So when you refer to some online content, you see encoder, decoder, but now we're all talking about decoder only, and then you might be wondering, what is the discrepancy? Well, the decoder only network as shown to do as good as if it's a part of encoder and decoder. So you don't necessarily need an encoder. So these days we are all focusing on decoder, and decoder goes from left to right, or it's unidirectional. So next we will take a look at unidirectional language model. So here, how do we actually, more visually, how do we actually train this model, any neural network model? So we start with a special token X0. Usually we add something like BOS, or beginning of sequence. Then we feed it to our model. It gives some prediction. Now we already know what should be the next word. Assume this is your training data. Since we have the entire input sequence, we try to see if it can predict the next word, right? So, and we compare these two and produce some kind of loss. Usually we use cross entropy loss for this. Then we already have the next word. Then we do the same thing. We run this, think of it, we run it in a loop, for instance. For RNNs, we saw it reuses state from previous computation. It uses state. Now we have a new input. It uses the previous state, and then it produces a new prediction. But we already know what should be the next word because we are looking at the training data. Then we compare it. Did it get the correct answer? Then loss is 0 or very low. If it got the wrong answer, we have higher loss, and so on. So at the time step t, you would see at time step t minus 1, you get the previous state, and then you predict, and then see if it produced the next token, in this case xt, so on for xt plus 1, and so on for xt plus 2. So in the end, if you keep running this, then you would reach the end of the sequence. We will have a special token. Xn plus 1 would be a special token called end of sequence, and the model has to produce end of sequence. So what we have lost a scalar value at every step in our time sequence. Then we would compute, say, average across this time dimension. So I didn't get into the details of the cross entropy. I think that is something you should look into if you haven't already come across this. This is the very popular loss function we use for training language models as well as any classification models. So here I'm indicating arrows in the forward path. Once we have the loss here, which is in this case, I showed it as an average across all the time steps. Then the reverse path is the backward propagation. So assume all the arrows are reversed, then the gradients flow the backwards, and then we have an optimizer step, which will go and make some adjustments. So I think, yeah, these are all the standard deep learning approaches. Then how do we do inference? So in the training, we said we pick the next sequence, next token, and then we just compute the loss. But in inference, we just pick, for instance, the best probability, the item with the best probability. And then the idea here is we stack too many layers and make it deep as possible. So that's our deep network. So here I'm showing just 2 layers, but this can go up to 100, for instance. Now, okay, so this is the core idea of language models. We saw how simple language models are trained, and so different kinds of, so briefly touched the different family of neural networks. Now let's look at the making language models big. So how, in this case, how do we actually make them big, or what, when we say big, what exactly, more concretely, what exactly? So first things we can make, think about making them big is increase the hidden dimension. So I mentioned in the beginning, every word we map them to embedding. And I said there is an embedding matrix, then we look up a vector. Now the size of that vector can be 500 dimensions or 10,000 dimensions. So 10,000 dimension vector is definitely bigger than 500, right? So that's one dimension, one aspect how we can make it big. The second one is number of layers. Now here I'm just showing 2, but think you can stack say 50 of these layers or hundreds of these layers. So that's another way we can make them big. And the third approach is supporting longer sequence. So sometimes, so here I'm just showing generic term n, but what are some practical sizes of n? So n can be just 200, or it can also go up to 1 million. So the sequence can be as long as 1 million. So we will consider exploring ways to make them big, and then what problems we might face if we try to make them big. Just to recap, we are making language models big in terms of 3 dimensions, the three properties. One of them is hidden dimension, that's the embedding size, the vector size. The second one is number of layers and sequence length, but then it's not so straightforward to just simply increase them. So if you try to do it, then we will run into some problems. One of them is exploding and vanishing gradients. So if the sequence length is too long, or if the layers are too deep, we would run into this problem called exploding or vanishing gradients. Basically, the networks assume they are all getting multiplied. The gradients are multiplied. And if the gradient is close to 1, then you're good. You keep multiplying 1 and you have 1. But let's say you have the gradient is 1.1 and you multiply 1.1 1,000 times versus 0.9 if you multiply it 1,000 times. So you would see either it grows to a really big number or it goes to a really small number. So that's the exploding and vanishing gradient problem at high level. Then when we increase the dimensions and increase the number of layers, that means we need more compute and more memory to train these models as well as to use these models. Then when we increase this, we are also increasing number of parameters. Apart from increasing sequence length, if you just increase the number of dimensions or number of layers, we are increasing number of parameters and we need more training data to learn this. So some of the solutions for this is the first solution is transformer architecture, which solved a bunch of these problems. One, training these models, bigger models with RNNs used to be really slow, and longer sequences could cause exploding and vanishing gradients. But transformers made it parallelizable and it addressed the gradient problem. Then I just mentioned we need more compute and more RAM. But for the past 10 years or so, we should look at how fast the GPUs are getting. So there is so much innovation in the hardware world for the past 10 years, especially in the hardware for deep learning, that they became so fast. I will briefly touch this part. And then data, language models don't need too much special data, so we can crawl the entire web. We all assume web is big, and let's go crawl it. And that's what the researchers have been doing. We crawl the web, extract it, and that's our training data. So you need more data, get the entire copy of the web, extract it, and fit the model on the whole data. So some popular corpus like training data like Common Crawl, dumps, and FineWeb. So this is what many are using to train these models. Then, okay, so let's take a look at the transformer. What exactly did it, I said transformer somehow made things parallelizable. How exactly did it make it parallelizable? So this figure I'm showing pre-transformer neural networks, say RNNs. What we see here is we see in the blue boxes, I have some numbers. So if you were to run the forward pass on this, we would see the numbers. So first there was a sequential dependency because the hidden state was shared between the time steps. So first we have to compute the box 1, and then the hidden state from 1 we have to use that state to compute 2, and so on. To compute the last step, we needed all the previous states. So you see there's a sequential dependency. If your sequence is 1,000 steps, then you have really 1,000 iterations to get to the last step. And maybe you can parallelize and compute the next step without having to wait for the last step in the first layer. But generally, I think there was a bidirectional dependency sometimes. So usually we compute layer by layer. So for longer sequences, it would take a long time to train the models, especially on longer sequences. Like if sequence is 200, then this would take 200 steps to compute. So over time, we are moving on to really longer sequences, like 8,000, 1 million. So what transformer did is it removed all these arrows that I'm showing in the red. So it got rid of those dependencies. Then instead, it came up with a concept called multi-head attention, or attention in brief, to recompute the hidden states from the input. So here I'm just showing the red arrows from the first one. Assume the arrows are there for other inputs. So we got rid of this sequential dependency within the layer, and then we recompute them at every step by looking at the input. So now we can compute the step at x0 as well as xn at the same time because there is no dependency between them, right? And then once we have this whole layer computed, then we can go on to the next layer, and then we can compute all of them in parallel because there is no sequential dependency between them. So this was a big deal. This made a lot of difference in training. This basically enabled us to train on longer inputs, as well as you can now train bigger models because things are so, the computation is so much parallelizable, especially when you tie it with the parallel architectures like GPUs. So that was the one thing I wanted to highlight, and keep in mind why we are all using transformer, and bigger models, why we couldn't do this before. So the next, the item, okay, so I'm going to touch the multi-head attention, right? So the key component here is how we recompute the hidden states. So this picture might say we got rid of hidden states and there is no transfer between them. Well, we still have hidden states, it's just that we don't have dependencies. We have to recompute the hidden state, and that is what the new term for that is attention. So how, I think at high level, what exactly is attention? So one way I would like to describe attention is it's a learned weighted average over a sequence. So you have a sequence, you have weighted average, and then you have, and those weights are learned. That's attention. So you have a sequence, let's say x1 to xn, then what's the simple average of this sequence look like? So you sum them all, and then you divide by the how many you have in the sequence. That's a simple average, correct? Then you do weighted average. So instead of simply summing them and dividing by the total, so in this case, every item in the sequence get the equal weight. So what if we have unequal weights to the sequence? So this way, if you don't want to use some item in the sequence, you set that weight as 0, then you ignore that, right? Basically, the model is not focusing on that item by setting the weight to 0. Whereas if something is important, you set higher weight. So that is the weighted average. So here we multiply by weights and divide by the total weights, sum of all the weights. So that's the weighted average. Then we do, okay, now what is the next step? So you notice we had this denominator normalizer, which is the sum of all the weights. What if our weights are normalized in such a way they sum to 1? So then 1 by 1, same. So we force the model to normalize the weights. So that would be 0. All the weights are in the 0 to 1. Assume it's a probability vector. So it just makes everything so easy to understand. So you see a 0, that means ignore it. 1 or close to 1, that means that is important. And then they all sum to 1, so normalizer, you can get rid of normalizer. So now the important part of attention is weights are learned. I think that's the part I didn't tell you in this slide. So the idea is, okay, we are computing weighted average and weights are learned. Now, how exactly weights are learned? I think anything in a lot of things in deep learning, when it comes to learning, is actually some matrix multiplication. Or matrix multiplication, you can also interpret it as like dot product between a bunch of vectors. And the weights are actually dot products. So, if you look into some of the, there are many guides online, but I don't think I can get too much details into this today. But this is a general idea. So first, we are learning the weights, but there are some dot products between the vectors. Think of them as all of them are embeddings now, and you compute the dot products between each other. So that's some kind of learned weights. Then we normalize them to 0 to 1. That's our softmax. So this was the core idea of transformers, where instead we got rid of the hidden state transformers, and then we learned weighted averages, and we call attention. Then it also said something called multi-head attention. Basically, we do multiple copies of this. It would use multiple weighted averages. It's basically running this all in parallel, multiple copies, sometimes 8, sometimes 12, sometimes 24. So that's the general idea. There are many online guides to understand this attention. I think the one I would like to recommend is just search for illustrated transformer, which visually explains how attention is computed. So you would see matrix multiplications to learn the weights, and then rest of the calculations are the same. Then the second core idea in the transformer was what happens if you stack a lot of layers. So let's say your network is now 100 layers. So remember the back propagation, the gradients have to go all the way from the top layer where we compute loss to all the way to the input. So that was one of the problems, but transformer solved it by using something called residual connections, also called skip connections. And then it also has some nice ideas like layer norm. So basically it addressed that problem. So now you can make it longer. You can compute on a longer sequences, provided you have enough RAM, all of them in parallel, as well as you can stack as many layers as you want. And that unlocked basically large language models, right? So now let's more concretely, I have been saying the terms like large language models, but how large did they actually become over the years? So when in 2017, the original transformer paper, what we call Attention is All You Need, published, the base transformer model which was called 512 dimension embedding, the vector sizes that we initially discussed. 512 dimension was considered base, and big was considered 1024 dimension. And remember, we also had encoder-decoder networks. So it was 6 layers, type of 6 layers. Even the big model had 6 layers. So totally we had 12 layers, and 1024 dimension was considered big. So in a year, 2018, transformers were still getting started. It was not fully recognized at the time. Not much progress. The model was still about 12 layers. Then you fast forward to 2019, when GPT-2 was announced. Now so it has a family of models from small to small, medium, large, XL, large, XL. So on one end, now 12 layers and 768 dimension is considered small. On the other end, now XL is 1600 dimensions, but 48 layers. Now instead of 12, now you have a stack of 48 layers. In 2020, when GPT-3 was announced, the large was now 12,000 dimensions and 96 layers. So we quickly grew from what we called 12 layer, 1000 dimension as big, to now we are looking at models that are 96 layers and 12,000 dimensions. And then OpenAI stopped OpenAI stopped describing models in depth, so we don't know how big the new models are. So with this progress, models become really expensive to train. Right now, if you think about how big this GPT-3 is, it's really big. So we can't. It costs multiple millions of dollars to train these models. That's like orders of tens of crores rupees. So that's quite expensive. And then usually in a research, like when we are experimenting, not all ideas turn into a useful idea. Sometimes we try something, it just doesn't work. So, and now every one of those experiments, we are looking at millions of dollars. So experimentation now becomes so costly. You could train a small model, but that's not going to move the needle. Big models are quite expensive. So we walked into this territory. Now I think now onwards, I think until now consider it was all intro. Now we're going to touch some research ideas. So what are some cool research topics going on at this time? So the first one you might hear is scaling loss. So here the key problem we are trying to solve is, okay, one, experimentation is very expensive. Can we predict performance of some experiment without me having to train it? Why we do that? Because it's very expensive to do that, to actually train a model. So we are trying to predict the performance of some model without actually training it. First we train smaller models and then look at what if my model grows to this big and I have this much data. And then what would be my performance? So that's the one line of work that is talking about this exploring research ideas. So one research direction. Then second direction is distillation, where we create, first we train big models. Training is one thing, but we also need to run them in production somewhere. For instance, say OpenAI or Google or Microsoft, some big corporation trains these models, but then you want to use them. Some of the models are open source, so you can download and run them. To run, also, you need really expensive GPUs. So even using them is very expensive. So distillation, this is an approach where we try to create smaller models that almost approximate the big models' performance. It's probably one of the very coolest ideas at this time, because considering how models are big at the moment, a lot of people are working on distillation. For instance, you want to push a model to a phone, and then it has to fit in a phone, or it has to run on a laptop. So this is one line of work that's still going on, and improving transformer efficiency for long sequences. So RNNs were, well, not so easy to train, or they're not so fast to train, but they were really fast to run in inference. So there is some line of work trying to optimize that. Maybe we'll skip that part. So next thing we see is compute. I think this is a bit at the hardware level than the software level. So we discussed that transformers became more parallelizable than the previous models, because we were able to compute all of them in parallel. And parallel architectures like GPUs instead of CPUs were really helpful to train these models. In 2017, we were looking at GPUs like NVIDIA V100 that had 32 GB RAM per GPU, and then it had 15 trillion floating operations. But then fast forward 5-6 years, now GPUs have gotten big, like 32 GB to 60 GB RAM, and then 15 to 67 floating operations. So you see the compute is getting faster and bigger. All these calculations under the hood in higher precision, like full precision, like 32-bit. So it turns out 16-bit precision is good enough. So why we care about 16-bit? Well, it takes less memory. You are using fewer bits, and it's faster. So the newer models are all trained with lower precision, and the newer hardware. So Google and NVIDIA and a bunch of other companies sat together and pushed for this new format called bfloat 16, which is a better 16-bit precision, which was invented for deep learning. And there have been tremendous progress in distributed computing, especially with GPUs, like how fast they can communicate when you put 8 of these GPUs in a node versus you have, say, thousands of these nodes, all of them talking to each other to share gradients. So there's been so much progress and focus on this. If you are excited about a bit more lower level stuff like hardware, so this is really an exciting time. Then that's the training optimization. Oh, I mentioned 16-bit. I will talk about bfloat 16. So all the new hardwares are come up with this new format called bfloat 16, which is, for instance, 2015 we were using 32-bit precision to train models, but we discovered we don't need that much. And then how about we do it 16-bit? Now, if you look at how many operations we can do, we went from 15 trillion operations to almost like 2,979, almost 2,000 trillion operations, just in the matter of 5-6 years. So that made a huge difference on how fast we can train models and how big of the model we can train. Inference optimization. So this is about training. This is 16-bit floating arithmetics. Then inference time, we found that we don't even need 16 bits, and we don't even need floating point arithmetic. As you might remember, integer arithmetic is even faster than floats, right? So we discovered, okay, so how about we run inference in 8-bit integers? And you see all the new announcements, some of them, they're talking about exaplus, some of them are just talking about this integer operations. So basically, there has been optimization at the very hardware level as well as at the very low level of the stack to make them faster. Some research topics right now is edge deployment, so optimizing these large models to run faster at special hardware or maybe on phones. Quantization, so how do we take 32-bit, 16-bit or 32-bit floating arithmetics, make it work in 8-bit integer arithmetic, sometimes 4-bit. I think that I have even seen paper with 1 point something bits. So without losing the model performance, computing all of them in a lower precision. So when you see all these new models, you would see this model was trained on some thousands of GPUs for so many days. Then basically thousands of GPUs cannot fit in one node. So they have to have distributed training. And GPUs are notorious for failure. So if imagine you have 1,000 GPUs in your training setup and one of the GPU fails. Now what happened to your training? So the fault tolerance in such setup, do you have to restart the whole training, or can you adopt your training to deal with some of the failure cases? So that is also an exciting research some people are working on. And then hardware-aware code, faster matrix multiplication. So maybe I think there's two ways. More concretely, let's say you're picking the dimensions that matches register size. So for some people discovered that if you set some of this hyperparameter as a multiple of 64, your model is now so much faster than if you set some, say, a multiple of 63 or 65. Why? Because if you look down in the hardware, a lot of operations are done at 64. Maybe you have 64-bit register, 64 core, tensor cores. So stuff like that. So there is a optimization at the whole level if you like the hardware stuff. Then let's move on to the next item, training data. So training data is often sourced from web, but sometimes the data is not readily shared because of copyright and intellectual property. So they might be breaking some IP stuff. So they won't discuss, they won't give you ready to download links. But some people have done, some researchers have published data sets that you can use to train your own models. And overall, the data sets have gotten really big. So the common source of data sets is web. You just crawl, there are companies that crawl the web and gives you the crawl dumps. One of them is Common Crawl. Think of web as a lot of HTML files. Sometimes you get PDFs and other format too, but majority of them are HTMLs. Then there is cleaning process, then removing duplicates, selecting to balance domains. So this is still an active area of research. We're making data sets available. Some of the research topic here is majority of the web is English. So if you care about non-English languages, then we may have to step in to contribute some of the data sets, because if you look at these large language models, they aren't trained for Indian languages, especially because almost 90% of the data is English, and then there's a small percentage on English, so non-English. So the performance may not be great for Indian languages, and some people are working on changing this, contributing data sets, improving the data quality. So all these are active area of research. So I'm gonna skip this part. Then I mentioned we will take a special interest in studying ChatGPT. So until now, what we learned is, okay, transformers came, they made training possible, made it possible to train bigger models in a faster way. Then there was GPU revolution, we got faster GPUs. Then training data sets started becoming available, or we figured out we should just train on the web. Then 2022 November, ChatGPT came, And this was one of the very interesting moment in history of AI. So just to highlight how significant this was, like some people are saying, I just took screenshots of two random people on Twitter to make this point. The first one is like, it's one of the rare moments in technology where you see a glimmer of how everything is going to be different going forward. So something, ChatGPT, basically this person is saying, ChatGPT basically changed everything. Now it's going to be different going forward. And then the other person is saying, a new episode of Bitter Lesson, almost none of the research from 2 decades of dialogue, publication, conferences, and workshops lead to ChatGPT. So the second point, what I'm trying to say is, there has been decades, 2 decades of work on how to build chatbots, how to build models like ChatGPT, but stuff like slot filling, intent modeling, sentiment detection, hybrid symbolic approaches, or knowledge graphs, there was so much work, and it didn't use any of those. Those were not useful. They just did something clever. So a lot of things just changed. Either the entire line of research became, we don't care about it anymore, and yet they did it, and now everything is going to be different. So one of the key thing that was, or the key thing of ChatGPT is, which I'm going to tell you in a minute. So far, what we have been talking is, you train a language model, get the data from web, ask it to predict the next token, right? So then ChatGPT happened. So if you ask a model to just predict next token, will it be really smart? So one specific example here we have, let's say you ask the model, explain the moon landing to a 6-year-old in a few sentences. And the completion for that would be, it would just give you more questions, like explain the theory. Completion from a typical language model would be, explain the theory of gravity to a 6-year-old. Explain the theory of relativity to a 6-year-old in a few sentences. Explain the Big Bang theory to a 6-year-old. So basically, the model knows how to model probabilities, and maybe it just learned these things from a question back somewhere, and then it learned that these are the possible other questions you could ask. It didn't really understand that we are asking it to explain, right? Then in 2021, 2022, OpenAI worked on something called InstructGPT, and they did something where now when you ask explain the moon landing to a 6-year-old in few sentences, instead of just giving other ways you can rephrase it, it actually understood, okay, you're looking for explanation, you're looking for 6-year-old. And then it started producing something like people went to the moon and they took pictures of what they saw. So basically it's now explaining in simple words. So it became more intelligent in a way. So what really changed? So and the answer is, if you just make these models bigger and train on lots of data, we won't get here. So it's not, the scale is not the answer. So what really happened is they used something called post-training. So they made LLMs to follow instruction. So here the prompt is an instruction. We are not asking the model to complete the sentence. We are instructing the model to do something. Here the instruction says explanation and use the language of a 6-year-old, right? So this part, we couldn't achieve this in purely by training on the web. So now the training of the LLMs have 2 stages. The pre-training stage, basically everything we talked so far, and then an additional step of post-training. This step is called, this approach is called reinforcement learning from human feedback, or RLHF. If you hear this term RLHF, so basically it's an additional step on the language model to make it smart or make it follow instructions. So here there are many approaches to it. We won't get into all the details, but maybe we'll spend a minute or so looking into what exactly RLHF do at high level. Before that, okay, research topic. So this is one of the very exciting or hot research topic at the moment. So the other word for making this follow instruction is sometimes called alignment. So basically making LLMs align with human preference. So on any given day, we prefer this output than the bland output here it gives, which is just giving a rephrasing of what I just asked. So sometimes this line of work is called alignment, and a lot of it's one of the hot topic at the moment. Then guardrailing. So this is also the stage where we make LLMs be safe and not talk, not suggest dangerous things. This is the stage where we do the post training, we guardrail it, and safety stuff. I don't think I have more to say about these things, but okay. So RLHF. Let's take a look at. How are we doing on time? Okay, RLHF. So let's take a look at RLHF, reinforcement learning with human feedback. So until now, we talked about take a transformer model, make it big, train on the whole web. So that's our base model. Then in this stage, we collect labeled examples where we expect the situation like this. For instance, given this prompt, we ask humans to produce this output. So we collect these examples where prompt and expected output. So that's the instruction data set. Basically, treat them as this is the instruction and this is the action or the completion for the instruction. Then we here we use labelers to produce a bunch of instructions, and then we ask now we train the model on the instructions, specially created instruction. If you remember, so far we trained on web. The data could be useful, or it could be, it could be truth, it could be noise, it could be, fake news. We don't know what it was. But at this stage now, we are only training on the good quality data that we know it's useful. Then once we fine tune, so this is fine tuning, basically continued training where we swap out the web data set and put in our carefully created data set. Then once we have fine tuned that model, then we sample or prompt and sample a bunch of outputs. So sampling, basically, instead of selecting the first one best of every step, we might not necessarily pick one best, but in the top 5 or top 10, we pick one random one, for instance. So then that will yield multiple possibilities. So if you just pick best every step, you get the one output. You get one of the top 5 or top 10. Then and then you complete it, so you get multiple choices. Then we ask humans to rank them, and then we train a new model that can rank these candidates. You remember in the very beginning, I mentioned there are two kinds of problems. One is a completion, other one is a ranking. So this is basically ranking. So we are asking the model which of this is more likely. So we fine tune this model to rank these possible ABCD candidates and follow the human preference here. So now this is a reward model. Then we will have a reinforcement setup where we have a model can generate some outputs, and then we have a reward model to give us the score, whether it's a good one or the reward for that specific output, and then we run it in a reinforcement setting. So that's at high level. So now with this, I would like to touch on a few topics, few more active topics. We use, so until this instruction fine-tuning and the LLMs approach, also until that point, most of the LLMs were open source, so you could download them and run them. For instance, GPT-2, you were able to download it and run it. So then a lot of things changed. So until now, just a recap is, if let's say I have a language model and I want to make it good for Kannada, for instance, I would take that language model and fine tune on Kannada dataset. Then there were techniques to do this, like low rank adaptation and parameter efficient training. So where basically you don't fine tune all the parameters, you selectively fine tune a subset of parameters. Now with this, a lot has changed in the past few years. Like you don't always get the weights to these models. So even if you do get weights to those models, something like Llama, for instance, from Facebook, they are so big, it's difficult to train or fine tune them. So you could do it only if you have, say, hundreds of really high-end GPUs. Otherwise, it's really not possible. So, but there are ways around it. One of them is prompting. So instead of fine tuning, you could describe what we are trying to do. So for instance, I want the model to translate from English to Hindi. I can describe that clearly in the prompt. And then, so this kickstarted the whole line of work called prompt engineering. So now we are, instead of fine tuning the model, fine tuning basically means, okay, download the model, create your data set, and then continue training. So instead of doing that, we are now packing the examples in the input or in the prefix and showing this is how it is done, a few examples, and ask the model to complete it. Okay, so this is still an active area of research at the moment. What are the limitations? How to effectively do this? Then this also, along the same line of work, you would hear something called in-context learning. So where prompting you don't always have to show examples, but if you show one example, how much would be the performance? So if you don't show any examples, what's the model performance on some task you're trying to do? Say English to Hindi translation, I don't show any examples. I just ask the model, translate English to Hindi. Prompt engineering is like translate English to Hindi, but don't assume common sense about model having common sense. You have to say it explicitly. This is what translation means. Translation means it should preserve all the meaning of the source. It should not add anything extra. It should use only Hindi's letters. You know, for a human, you would just say translate English to Hindi. But for a language model, you have to say it out explicitly. So you spend a lot of time crafting this perfect prompt that does all these things. So in-context learning is, along with all these things, then you start showing some examples. The model might still not get it because it might not have seen the task in its training. So in that case, we show a few examples. So what if I just show one example? What if I show two examples? So this is the in-context learning line of work. Usually I've seen sometimes the model don't do well for zero shot. That means you don't show any examples and you don't do well. But you show just one or two, at most 5 examples, and it really gets good. It gets good performance. Then another line of work is chain of thought reasoning, where we carefully create the prompt. We also show few examples, but then we ask the model to think through or to show the intermediates work. Instead of just giving me this is the answer, it has to show this is how I got to the answer. So this is useful if there is any reasoning. Let's say you ask the model to solve some math problem. You could just ask more, and it would just give you an answer, versus now it will show you the steps it took to give you the answer. So this usually improves the performance. If you force the model to think through and show it's the intermediate results, usually it improves performance. Okay. Then in the past year or two, then the new development in the LLM world is we went to multimodality. Okay, so what multimodality means? So now modality here is text or vision or audio. So until now I've been only talking about text, but there has been some work showing you can use transformers to do process images or audio. Now all of them were put together into one big model where so you can input image to the model as well as describe something in text. So everything is handled in one model and it can reason across. So I think this is the latest development in the LLM world. Along this direction, I think when I was in grad school, I was just trying, in 2021, I was just trying to make these models translate 500 languages. For me, okay, that was many years ago. But now we're going not just languages, not just languages and programming languages, but also images, video, and speech. So you could, for instance, you could just upload a YouTube video and ask questions, and then ask it to produce some diagram or some summary in a visual format. So it could process the video, understand what you're asking in the text, and produce an image. So I think it's pretty amazing. So this is some new development. I think I won't be able to go too much into this. Still have 10 minutes. Okay, cool. So the next item I want to discuss is evaluation. Right now, I think in AI world, everybody is working toward building better and capable models, and we have started using LLMs in our day-to-day work, our day-to-day life. So now evaluation is more important than ever. So sometimes you see models are not evaluated in a very reliable way. You would see some benchmarks are picked. So basically, how do we evaluate models? We have some benchmarks. Some benchmarks I would like to say are, so holistic evaluation of language models. This is from Stanford. Hugging Face have a open LLM leaderboard. So basically, there are benchmarks. What does exactly a benchmark here mean? There are a set of tasks, and we put this LLM to for a test on a set of tasks, not a single task anymore. Earlier, let's say we only cared about translation models, then we would just evaluate on a translation data set. Now these models can do almost everything. It can translate, it can reason, it can answer questions, it can do a lot of things. So we have to have a representative set of tasks, and we evaluate them on a set to assess how good of this model is. So there are so many of these. There is no one go-to answer at this time. It's a bit chaotic because everybody is trying to do their own evaluation. I think that's a good thing. So the more people look into it, the better it is. Currently, this is a really active, ongoing research area, and more people are looking at in improving the coverage of the benchmark task. By coverage, I mean I said it's a set, but how big is the set? Usually some 10 tasks, but does 10 tasks, are those 10 tasks good enough? For instance, all of those 10 are English, for instance, then does that mean it will work on Hindi? So then you might want to add Hindi task to see, will it work on Hindi? Or will it work on Kannada? Will it work on some Indian culture-related stuff? So those things, many researchers are trying to expand it. That's why there are so many benchmarks, and I've only shown 3. So there is a lot of evaluation about whether the language models are fair and whether they are safe. Does this produce any content that is not safe for children, for instance? All those things are still active area of research. So here is a screenshot from Helm. Basically, the evaluation look like there are 10 tasks: narrative QA, question answering, open book, closed book question answering, MMLU. I think that's a multitask language understanding. Then math. So testing this on some math tasks. WMT, last one is a translation, some medical question answering, legal bench. So there are a bunch of these tasks, they evaluate it, compute the averages, and then rank them. And then in this, I took this screenshot recently, a day or 2 before, and you see they basically rank this model. GPT-4, for instance, on this specific benchmark, GPT-4 seems to be the winner. But then you evaluate it on a different benchmark, then you see some other model is a winner. But it will give you a general idea of like how these models compare to each other on specific tasks. Okay. Then another line of work is the previous one I said, these are benchmarks created for machine learning models. Then there are also tasks created for humans. If the goal is at some point, we humans, the AI and LLMs are going to be as smart as humans or maybe smarter. I think that's the whole idea of AGI and super intelligence. So now how do they compare? How do these models perform on the task designed for humans? So here is a screenshot from GPT-4 technical report I took. And what we are seeing here is on the x-axis, we are seeing a bunch of tasks for a bunch of academic and professional exams. For instance, I don't know if you recognize any of these. There is a SAT math. So this is the math exam for students, GRE verbal and GRE writing and GRE quantitative. So these are some exams I had to take when I wanted an admission in a US university. I had to take GRE. So these are the same exams that I as a person would take. And then there is a Codeforces rating. I think I recognize this one. This is some programming competition. If you want a job in some big tech companies, they will put you to some coding competition. So on this one, it's not doing so well. So there are a bunch of these tasks. So you might recognize there's a task for chemistry professionals or students. There's physics tasks. There is macroeconomic tasks. So they are evaluating on this. This is taken from GPT-4. So I'm just trusting there's no contamination or anything. So you see they are getting better. So I think the blue bars are GPT 3.5 from 2022, if I remember. GPT-4 was 2024. So they are getting better overall. Excuse me. So in summary, we talked about language models. We talked about how to make language models bigger and transformers at high level. We talked about the key thing that changed ChatGPT, basically making them follow instructions. And we talked about how to use these newer LLMs to make it work in unseen tasks, like using in-context learning and forcing it to do chain of thought. Then we briefly touched evaluation. Then we also discussed some research topics, scaling law of distillation, improving the efficiency, then optimization. We briefly touched about training, what's going on in the training world. For instance, we are all training on distributed setup, where we are increasing the fault tolerance. And then we touched about data, increasing the coverage of data. Then post-training, where alignment is one active area of research. Briefly touched evaluation, but these are all my subjective opinion. Again, this is not exhaustive. There are so many cool ideas that people are working on. I just didn't have time to explore or cover all of those. Consider this as mere suggestions. Then we have a few minutes. So more concretely, I think I've been talking about a lot of stuff at high level. More concretely, I think it all comes down to what can I do? So where do I even begin? I think sometimes we all face this problem. Okay, so I want to do something with LLM, but I don't even know where to start. I think for those, if you have that question in mind, this slide should be useful. First thing is, there is this company called Hugging Face. You may have heard of it. All the open source LLMs are here. People release the models from the Hugging Face, and we use Python. If you have not already learning Python, use learn Python, and there is a package called transformers. And then in that Python library, everything gets easy. You can do all the things we discussed using this Python library. Something like, for instance, so you import transformers, it's Python, right? Everything should be easy. For instance, we create a transformers pipeline. In this case, we are loading one specific model, Pi4, which is a recent LLM from Microsoft. And you can, if you want to query the model, this is how you can send the messages, and then it will produce an output. So just to get started, if you're confused and where to get started, maybe most of you already know. So just reiterating for those who might be confused, just get started with the transformers and play around with this library. Spend some time with Hugging Face models. Then yes, we are like to answer any questions. I will send these slides if others would like to access it. Are there any questions? Okay, so I'm seeing the messages now. Sorry, I didn't see any messages before. All right, thank you for joining.
Thank you so much, sir. Thank you. On behalf of everyone here, I want to sincerely, graciously sharing your knowledge just today. We appreciate the effort to work to this session, making it both informative and engaging. Thank you so much, sir.
Thank you. It was my pleasure. Great to be connecting with my alma mater again. Thank you. See you all next time.
Dear participants, please do fill the feedback form. It is shared in the group, the chat box.
Thank you, sir. Thank you.
So we look forward to having you all back tomorrow as we continue this journey of growth and learning together. Thank you. Thank you, one and all.